Okay, so welcome everyone. Yesterday, in the previous session, we had some introduction to the optical fiber or fiber optics topic. One thing, more than one thing I'm going to say is that you might notice that the fiber is spelled both ways, and sometimes I'm just not confused because I'm way beyond the confusion state at this point. I stopped trying to figure out which one is the correct way because I can see that many different companies and different sources spell it both ways. Sometimes they spell it fiber and sometimes they spell it fibri. So it's just one little thing. And you might notice some of my materials are being spelled both ways because I want to satisfy both parts of the both hemispheres. All right. Now, one thing before we start part two, which is the practical application of that, I'm going to just point you to one thing. And let me just get the... you should see my Photoshop, my greatest piece of art right now. What this represents is, let me just get a better pointer. This is, let's say this is a multi-mode optical fiber. So over here we have the cladding, we have the core here, and that's where all the light travels through. And this core is cladded or surrounded by the cladding. And from yesterday's lesson, we found out that the index of refraction is greater in the core than it is in the cladding. And it's glass. The whole material is glass, which means that the core is slightly more impure. It's just made on purpose, a little bit doped with some slight impurities in order to increase the index of refraction, which means that when the index of refraction goes up, which is higher in the core than in the cladding is lower, that means the light is going to travel slightly slower in the core than it would in the cladding. This way of solving things ensures that the light is actually being kept in the core. And as we talked about, if you were able to shrink yourself into one little person, like, let me just see here if I can draw that. Let's get more art. If you shrunk yourself and walked into this core, if you were just walking on it in the core, all right, you would see what you would see that you would be surrounded by a tube made out of mirror, right? Okay, that's good enough for the for my beautiful art. I don't think I'm going to cash on this one here, so I'm just gonna keep working. All right, so here is the problem with multi-mode. Let's say we have a beam of light, and multi-mode mode is a ray of light. So if you have a light bulb, for example, just a light bulb, let's see here. Yeah, here is the thread and here's the light bulb. All right. Now, the light is going to shine in all different directions. Okay. So these rays are, that's when we talk about modes, we're talking about each of those rays. Now, how many of those rays? Well, it's an infinite number of rays because it's just one common kind of a glow, right? But in order for us to picturize the mode or the moding or the modes, we're just going to draw things as some, chosen randomly rays or modes. Okay. Now let me just erase this thing here. Can I do this? Oh. All right. We're going to leave it here. Because I would just get a blue background on this. All right, so let's say we have different number of modes, because this is a multi-mode. So there will be like a laser diode. It will be a LED emitting a light and shooting the light into the core under specific types of angles. So it's not going to exceed the critical angle. So the light just keeps traveling in the core. It doesn't escape through the core. So here is the little bit of a problem. Okay? Let's say, well, one of the modes is going to be light going straight through it. All right. Now let's say there's another mode that enters the core at a different angle. Okay. So it's going to keep bouncing off the interface between the, and let's say here, all right, at the same time, these two are going to get to the end, and the longer the cable is, the bigger the difference is going to be. So this one that goes straight, it's going to get quicker to the end than that one. So what happens is that if you insert a light pulse like this, here is no light, and here is a full brightness of the light. The pulse at the other end, because of that dispersion, because of that, this here has a longer distance to travel, right? And there's a bunch of other ones that do the same thing, and some of them cover more distance, some of them cover less distance. So the pulse at the end would look something like maybe dispersed a little bit like that. Okay, so that's because of the dispersion. All right. Now, so that is because there is a difference of indexes of refraction. This is considered a step index type of a fiber optic strand or conductor. We are stepping the index from one environment to another, and the step is immediate. The change is just basically from one to another environment, and it's just a dry cut kind of a thing. Right? Now, to resolve this issue, somebody smart got together with somebody else who is also smart, and they came up with some sort of great idea. Let's say if the index of refraction was not clean cut from one place to another, but let's say towards the center of that, it would be the number would be the greatest, and the core would have a graded index of refraction towards the cladding. So the index of refraction would just decrease, right? Not increase, but decrease towards being a smaller number as you go outward from the middle, and the other way as well. All right, let's see here. The index would go down, the number would go down. Okay. What does that accomplish? Well, what happens is that if anything that travels in the center would have the slowest speed, but if there is anything that travels anywhere outwards toward the center, from the center, then the speed of the light traveling through that would increase in this spot here than here. So this would be the slowest. This would be a little bit faster. And as we go outwards from the center of the core, the index is graded to be less and less and less. So naturally, if the index is less, the light is going to travel faster. And here's a band saying, so that would sharpen that signal so everything arrives at the same time, question mark. You got it. That's the whole thing. So what happens now We got a light beam. The whole point is to slow down, because we can't speed up the light in this environment, but we can slow the fastest one down, so to accommodate the travel time that the other ones have to cover. So in this case, here would be the straight one, that the beam of light, or the ray of the light, or the mode traveling through the center. And then as we go under different angle, this light would kind of speed up a little bit comparing to that, and it would kind of look like a sinusoidal wave more than just sharp edges. All right. And they would arrive at the same time. Okay? And then when you have another one going through the same thing, and they would kind of like meet at those interceptions. So that's what would look like. So, and also they would arrive at the same time. So if you have a pulse here of light, it would maybe get a tiny bit slower, but not that much. But it would, for the most part, be resembling the original pulse of light. So the previous scenario would we would consider something as step index, because we are stepping from one index to another. And this one here is called a graded index fiber, because the index is slowly basically decreasing in number as we go towards outside. So you're going to hear a lot of that terminology saying graded index fiber. And it only works with multi-mode, because single mode is just having a one mode, so there's no need for having a graded index there. Okay? Of course, the multi-mode the multi-mode are shorter distances. For example, up to about different, as I say, different sources are going to tell you different information. And why do I say that? Well, it depends on when things were made. It depends on what equipment is being used, and basically, that, right, the transmitting and receiving equipment. But for the most part, this multi-mode wire is being used in LAN configuration. Some sources will tell you up to about 2 kilometers or something. We're going to analyze that a little bit for the most part. 500 meters is the probably the most common one. Like, for example, if you have IDF, which stands for Intermediate Distribution Frame, which is a communications closet with a bunch of patch panels and switches. And also it will have a media converter that would convert everything into the fiber optic signal. So the intermediate distribution frame is going to be strategically placed in whatever building to accommodate the distance of no more than 300 feet end to end, so the copper wiring can be distributed to the cash registers, to the phones, to PCs, wireless access points, and whatnot. Okay, and then those are further away than 300 feet from the MDF, which stands for main distribution frame. So then the whole thing is converted into fiber optic, into the optical signals through something that's called a media converter, and that is connected with the fiber optic. And there could be, usually it's about 500 meters, no longer than that, but you can probably go to. Now, do photons interact with each other? Well, from what I know, is probably okay. But glad you asked that question, because in this lesson we're going to discuss some sort of interaction of the photons, but not with each other, but with other things that they meet on their way when they travel. So do they interact with each other? I don't know. You would probably have to talk to some higher scientist. I'm pretty sure if one bumps into another, they're going to stop for a while and talk because, well, photons are, well, from what I from what I know, they are particles and they are traveling with certain frequencies. So light is particles and frequency. So if it's a physical particle, then if they bump into each other, they could probably interact in some sort of way. I hope I can't give you that vague sort of answer. I ask because if they are the same speed but across paths, they would collide. Well, here comes the CERN idea, all right, with the colliding particles. So they probably would. Okay. All right. Cool. Let me just bring that. All right. So this is today's lesson here. Can I? All right. It works. So today's class is fiber optics practical applications. Now, in the time that we have for this class, I'm just going to give you that basic information so you have some sort of anchoring point so you could study things further. Or if you find yourself a job that you're going to be further trained as far as particular tasks, then you're not going to be completely green in this topic, all right? We are going to have certain practical activities, which we call them labs. We are going to perform something that's called a fusion splice. And maybe if we have enough time, I'm going to show you some of the mechanical splicing as well, because both of them are important. Both of them are important. All right, so fiber optics, practical applications. What do we see here right away, right off the bat? Well, that looks like a patch panel, right? Well, it kind of is, right? It's fiber optic tray, a patch panel. Then you have the through connectors or couplers, optical fiber couplers, and you put optical fiber that is terminated with a connector. You plug into one side of the ferrule connector, and then the other one you plug into here, and they would mechanically pretty much be aligned and joined so they can pass the light through. So that's one of the ways of doing things, right? And this, from our class when we talked about rack spaces, this looks like 1U rack space fiber optic tray because it takes one rack unit. We'll talk about that as well as we go along in our wonderful trip here. All right, so today we're going to discuss cable types, fiber optic cable types. We're going to discuss something called loose tube, tight buffered, and a ribbon. And as a bonus, or not really a bonus, because you need to know that, we're going to discuss some of the connectors. And remember when I showed you that there are certain frequencies that are associated with fiber optic transmissions in the infrared range, but there are certain frequencies that are being used, not others, excuse me. I'll show you why. And that comes with the photons colliding, interacting with the medium that they travel through. Okay. All right. Loose tube cable. All right. Remember when we had that little picture of how, well, in the middle there was a core. It was surrounded by the cladding, and it was surrounded by the buffer. And then from then on, it would be surrounded by whatever needs to be applied in order to keep that optical fiber safe. Well, where do we see the optical fiber strands? Here's one. Here's one. Here's one. Okay, so there's few of those in this tube, and they are inserted inside that tube loosely. So that's why it's called loose tube cable. Now, right in the middle here, we have the loose tube. Loose tube. We have the strength member here. Where? Hold on. Where's that thing? Oh yeah. So no. Well, here's we have the strength member here. It's just a thick piece of PVC material or some sort of a synthetic thing that makes this whole cable well, nice and intact. Right. What do we have around inside that? We have something that's called tubes, and those tubes go all the way from one end to the other. And in these tubes, there are optical fiber strands inserted, and they're just floating loosely. Now, these tubes are also filled up with thixotropic jelly compound, right? And the thixotropic gel has certain properties. The more it is abused, the softer it gets. And then when the physical abuse stops, then it comes back to its original shape. That has to do with the environment, because those loose tube cables are, for the most part, they're being installed outside. And I'll show you some of the examples where they, well, yeah, how they are installed outside. These are the cables that carry the signal from one part of the city to another, from one city to another, okay, or from, well, basically they are being used outside. So they have to be protected against the environment, and they are installed where they are. As they are installed, they are day and night, all seasons through the year. So sometimes it's pretty hot, and sometimes it's pretty cold and whatnot. So the thixotropic jelly takes care of the temperature differences pretty much, so that there's no freezing going on, or expansions and contractions that would damage those cables due to the temperature changes, as all materials expand and contract when the temperature changes. So that's why those strands are inserted loosely there, so they have a lot of playroom, so they are not squished. And then just to provide extra cushioning, that thixotropic jelly. So if you strip that cable, you're going to have your hands messy, okay, with that goo, that jelly there. Right? All right, so 1, 2, 3, 4, 5, 6 tubes here, strengthening member, and then there's water swellable. It's surrounded by water swellable tape. If there used to be some commercials of some kind of a camping gear. It would be like tablets. They look like lifesavers, kind of like candy in a little tube, and that would be compressed into a candy-like shape. And then if you put it in the water, this thing just expands, and you have a huge kind of like a handkerchief type of a paper towel or something like that. That's this whole thing here. This thing absorbs water, so the water does not get through, and it absorbs the water. How it does? It absorbs the water like crazy. That's the non-technical. I know it's like a non-technical tape, but it's a very, very efficient material that can absorb water and then can give the water back. Right now, there's that outer jacket also, and usually it's black, and that is a huge, thick type of jacketing. You can't just use your side cutters to strip that. It involves certain other tools that really can cut through this thing, and you can step on a pre-product and probably run over with a car. And this optical fiber is going to maintain its integrity. So here is the idea of loose tube. There's another sort of loose tube scenario, which we're going to go take a look at few slides down the road with this presentation here. Now I have included some sort of terminology here just because it would be nice to include that, but for the most part what we need to understand is what I just explained to you. And if you want to go further, here is the terminology you can research, and if you really want to get cute about that, you can go further and explore that if you want to get really scientific about this. All right, next slide. This is also picturizing the differences between polyethylene and polyvinyl chloride, PVC, PE or PVC, and it just describes the reaction to different environmental type of, well, I would say abuse kind of a thing. All right. So looks like according to this chart here, let's say what's the temperature range that between PVC and PE? Well, PE can handle from minus 55 to 600 Celsius. Right? PVC from minus 10 to plus 60. Well, this one wins. All right. Can it be bent to while it's cold? Well, it's bendable excellently, and this one is just bendable goodly. All right. It's lighter. The conductor, well, we can skip this one here because we're talking about optical fibers, not copper fibers. Insulation thickness, it's much less thick. It's thinner than that. So yeah, and of course the weight is going to be less. Moisture resistance, it pretty much scores higher. PE scores higher. Then, of course, all that technology, and there's a mouse or a rat that's just going to come there and it can destroy the whole thing. All right. All right. And here's a little explanation of what thixotropic means, so you can read that if you want. I'm not going to. I just explained that to you, but if you want to go further with that, you can pursue your knowledge. All right, loose tube cable. That's what it looks like. Now it's designed for harsh environmental conditions in the outdoors. Right, fiber strands are floating loosely. Fiber strands are floating loosely in the designated rugged tubes. So these are the fiber strands, and these are the tubes. Notice they're color coded as well. The tubes and the fiber strands. Oh, wow. Material contraction and expansion due to temperature changes will not affect the fiber strands because of the way it is constructed. Why is it not going to affect that? Well, because they are inserted loosely. They have a lot of playroom here. Plus, they are also filled with a thixotropic jelly that is also going to provide some reactive cushioning to the environmental changes, mostly temperature. Where is it used? Used mostly in the outdoor, long-haul installations, and different sources are going to tell you different things. Well, about 120 kilometers is as far as this one can go. Way longer than 300 feet copper, right? Now, what kind of optical fiber is being inserted there? Well, it is single mode because of the long haul applications. Now, that's what things look like. Here, I'm pretty sure you drove or walked by these things hanging from the utility poles, and maybe you don't know what these are. Well, this thing here is called a FOSC. So there you go. You can impress your girlfriend or impress your boyfriend saying, hey, look, I know what it is. Well, it's FOSC. Wow, okay. You can score some brownie points with that. FOSC stands for fiber optic splice closure. What's inside there? Well, there are optical fiber, those loose tube cables, just like those ones, this thing here. That's this here. This is this. All right. It's installed well, watertight, airtight, whatnot. So this thing needs to be protected from the environment. And as the technology moves along through the years, the way of mounting this, installing these cables into the FOSC has changed. And of course, it's being made more efficient and easier. Right? I even included a little video here. So if when you download this presentation, you'll be able to watch how, for the most part, the splicing of that thing is done. Now, you're going to notice that there is a slack of that wire. The FOSC is mounted on the runs here, on the support, and that's where the cables are going. This cable can go that way, maybe 50 kilometers or 10 or 20 kilometers or whatnot this way. And the other one here can go that way, maybe another 10 kilometers or not. And there, over here, there would be maybe other cables that are splitting into different parts of the neighborhood. What you have here, there are those cables are being stripped. The strands are being pulled out, they're being rolled out in those trays, and they're being fusion spliced according to whatever plan needs to be. So the strands, one strand from one cable can be fusion spliced into another strand from another cable, put it in a protective sleeve, and just insert it into that slot that holds that would hold the protective sleeve, and the rest of the wire, the access wire, would be gently wrapped around using a macro band. Remember, we were talking. Somebody asked me yesterday, do the fiber optics have to be run all the time in a straight line? Can we bend them? Yes, we can. Of course, there's a certain amount of bendature that we can apply, but look, this is good, and this is single mode. And if there was if this was a multi-mode, you could also bend this thing that much. How far can you bend those? Well, it depends on the specifications of the cable, right? Of the strength. Vince says, looks like nothing is safe from the rats based on that chart. Yeah, that's a very useful chart. You know, spend all that money for all the protective technology, and there could be a rat that comes and just all bets are off. Or you can probably pretty much, I'm not going to do that, but if you could search on YouTube to see sharks are trying to bite through the fiber optic cable that's run on the bottom of the ocean. They also try to do that. So that's why there's a lot of protection needed for that, for those wires. Right? Now, fusion splicing, like I said that those wires or those strands are fusion spliced. Fusion splicing is, and we're going to do that in our lab, is basically taking one strand of the fiber optic and putting against another, like butt splicing, another one, and it has to be nicely cleaved, which means they both need to be cut to straight edge. Okay, and they're going to be aligned, so the cores align and the claddings align, and there is an electric spark being shot at that point where those things are touching, and it's almost like spot welding a glass, right? But this one is called fusion splicing. So now you know what these are. These are FOSCs, right? And this would be a loose tube optical fiber cable going some ways that way, some ways that it could be splitted, and some of the there could be different splitters installed, attenuators and whatnot, depending on where do you want to take the signal from the main feed, where it should be going, and at what strength, and where it should be split. So there's the FOSC. All right, now how is that? You can see sometimes that there could be like a service van right by that spot. So this would be taken off that, and there will be a slack of the wire enough just to take it down, put this whole thing in a van, and the van is basically a fiber optic lab on wheels, that the fusion splicing can be done, because you need nice, clean, and dry environment in order to do your job properly, because cleanliness is extremely important when dealing with optical fibers. Well, you're dealing with strands that the cladding is 125 microns thick, and if it's a single mode, the core would be 9 microns thick. Well, that core that transmits the light, the diameter of that core is quite comparable to the size of the dust particles. So if a piece of dust lands on that, it can actually blind the transmission. Now, it's affecting more the mechanical splices where there's no fusioning going on. But still, dust is our enemy. So, well, that's why those FOSCs are being taken down, put it in the van, doors closed, worked on, taken out, and hung back. Okay, hung back. All right, so that's about FOSCs. Now, we talked about the loose tube cable. Now we're going to talk about something that's called a tight buffered cable. Notice the jacketing is much, well, not as thick as the other one, and it's orange, and it's softer, and it's filled with armored yarn, or sometimes it's called Kevlar. Kevlar is the material that some of the bulletproof vests are made of. It's like a silky, well, you'll be able to touch that in class. Silky type of strands, like an angel's hair, kind of a, yeah. The purpose of that is cushioning. We can't use that outside because, well, it's tightly packed, and if the moisture gets in, and moisture always gets in, it would basically damage this whole thing, because things would freeze, things would be crushed, squished, and, well, made not good, right? And not good is not good. Good is good. All right, philosophical statement. Then there's, you can see the ripcord, and we all know what ripcord are being used for. Now, here is 900 micrometers buffer, or basically the jacketing of that. Then there's 250 microns optical fiber strand. If that's stripped, it can be stripped right down to 125 microns, right down to cladding, and then it can be worked on. It could be put on a mechanical splice, or it could be fusion spliced to something else. These ones here are designed for indoor applications. So to interconnect one communication closet to another. So let's say there will be 80 computer Ethernet links going into one closet, and those 80 Ethernet cables can be put onto one common optical fiber link. And I could use maybe 2 or 4 strands. If you were using 2 strands out of that cable, you would use one as transmit and one as receive, or one transmitting the signal in one direction and the other one transmitting the signal in the other direction. Quite often between the communications closet like that, there will be 2 links, so it'll be 4 strands, 2 transmit one way, 2 receive the signal. Okay? So mostly it's installed in the LAN environment. And because it's a tight buffer, it has to be inside, right? Tight buffered because it's tightly packed, tightly packed, to provide some sort of cushioning when handling. And those are quite soft to touch and to handle, but they have to be only installed inside. And for the most part, they're going to be multi-mode cables. Are they available in single mode cables? Yes, they are too, right? Fiber strands packed tightly within the armored yarn and wrapped around other jackets, more flexible than the loose, way more flexible than the loose tube, but also more fragile, right? Used mostly indoors in LAN environment, local area network environment. All right, tight buffer cable, LAN environment. This would be the patch cables that were made out of the well, tight buffered cable. Now, these cables are yellow, patch cables are yellow, which tells me that these are single mode. patch cords. If they were orange or aqua, they would be multi-mode. And we'll go over the color coding a little bit. Now, over here, these are Ethernet cables, and this would be here. So that looks, you see, oh, look, there's a strand, transmit, receive. And there would be some sort of Ethernet. So that looks like these are media converters devices here that would convert the Ethernet signal into the optical fiber signal. All right, now we looked at the loose tube. Then we talk about the ribbon cable. Ribbon cable is almost the same as loose tube, but there's a slight difference. Well, there's a quite significant difference. Instead of just dropping them in a bunch and shoving them down the tubes loosely, those strands are packed into ribbons. Right? So what did I write here a couple of years ago? Ribbon fiber optic cable is arranged into a strip. Right? So they're strips. A convenient solution for space and weight, well, challenges. You can, if you arrange those things in strips like that, you can pack more of those strands safely into a tube. Now look, 1, 2, 3, 4, 5, 6, 7, 1 to 12 here, right? Multiply that. That's just one tube. That's just one tube. This thing can carry a lot of data. How much data? Well, it's pretty much hard for us to comprehend with our human brains of how much data can travel through this thing here, but a lot. Right? The cable ribbons are actually coated optical fibers placed side by side, encapsulated in mylar tape, similar to a miniature version of the wire ribbons used in a computer wiring. A single ribbon may contain 4, 8, or 12 fibers, and they can be stacked up to 22 high. Now, when it comes to splicing those, some of the more expensive fusion splicers, they can also splice the whole ribbon at once. One whole ribbon to another ribbon. So, wow, the time efficiency when it comes to that is way goes up. Goes up way high. Efficiency goes, you know what I mean. All right, excuse me. Color coding. Now, color coding for the fiber optic strands. So these here, see, these are color coded. From 1 to 12, they go like this here: blue, orange, green, brown, slate, white, red. And I'm not going to ask you to remember this one here. If you work with that, it's going to come to you by itself. Blue, orange, green, brown, slate, white, red, black, yellow, violet, rose, and aqua. Okay, so here's blue, here's aqua. Now, from 13 to 24, they go the same colors, but with the black stripe, except for the for number 18, because you can't put a black stripe on a black wire, so it's kind of reverse. No, sorry, the number 8 here. It's just a negative of that. So that's how the color coding of because they also have to be numbered. You need to know what you're connecting from one end to another. These are the strands. Also, there are jacketing color coding as well. See here? This would be a jacketing. Now let's see. Jacketing. Yellow. Oh, single mode. Now, this is the jacket coloring. Now, the jacket is a little bit different because as the technology moves forward, better and better cables are being developed, fiber optic cables, and they have to be designated somehow. They have to be sorted or named or marked in certain ways. So here's what has been done. Okay, this is one of the oldest. You see here. See, here's a core and cladding size. That's an old optical fiber. 100 microns core and 140 microns cladding. It will be the multi-mode old cable. Also, because it's more rigid, it's in green, and it's using, see, there's non-military coding and there's military coding. All the rest, as you notice, all the cladding is 125 microns. Now, OM1, OM2, OM3, OM4, optical fiber multi-mode 1 was developed earlier, some years ago, 1970s or so. And it would have 62.5 microns core and, of course, 125 microns cladding. That's the only old cable commercially that would probably you still find, because some of the early 1970s or whatnot cables installed, they're still intact. They're still okay because they don't corrode. So you can still order some equipment that will accommodate this size of the core. Now, if you're later on, the optical fiber multi-mode 2 was developed, and it just has slightly better specifications, and all the cores here for the multi-mode are going to be 50 microns, and the claddings are going to be 125. So this is, first it was this, then it was that, then some years go by, somebody developed the technology improved, next one, next generation, and next generation, and they are being color coded. So for the multi-mode, that's 62.5, 125, orange jacketing. Then OM2 will have orange jacketing. I'm just losing the commercial, non-military here, and you can refer to military as well if you want. And then OM3, OM4 would be aqua jacketing. And then here, the yellow jackets right there, these are optical single mode. S stands for single mode, 1 or 2. So here's first generation, second generation of that. Okay. And here is approximately 8 microns, approximately 8 microns. So it could be, well, depending on the equipment and the cable you get, some of them you get 9 microns, some of them get 5 microns, right? And those are yellow jacketed cables. Right? Now, remember this chart? This was copper. And we cut 5E, cut. Notice maximum length, 300 feet, 300 feet, 300 feet. No more than 300 feet, depending on how fast you want to send the data, the transfer speed. Some of them can be only run so short in order to accomplish certain data transfer speed. But for the most part here, the maximum length would be 300 feet, not even meters, feet. So it's about 100 meters. Well, here's a chart for the optical fiber. Okay, let's see here. OM3, OM1, right there, 62.5. It can transfer 100 megabits per second up to 2,000 meters, 2 kilometers. All right. Now, OM2 can transfer up to 100 megabits per second, about 1,500 meters. And then here's 1 gigabit that OM1 can only go 300 meters. See that here? 1 gigabit per second, OM2 can go 500 meters. So here's some differences here, right? And then OM3, OM4, OM3, OM4, depending on, so they can transfer a lot of data, way more data, 100 gigabits, 50 feet, all right? 100 gigabits, 100 megabits, 100 gigabits, OM3, 100 meters it can traverse, right? So these are the multi-mode fibers. That's how you read that chart. And don't forget, here's all this blue area right here. Look, it just goes way off the chart. Single mode 1, single mode 2. Single mode can go way further and can transfer a lot of bits per second. Light is the winner here, Vince says. Yes. Single mode cable is a single strength, usually. Okay, so this is basically what we have said so far. It's just a summary of what I said. Connectors. Now, here's about 10 minutes to the hour. So I'm just going to keep talking because it looks like I'm going to go over maybe a couple minutes. So if you have to go, please go. And I'm going to post it later on tonight because I have another class to attend right after this. So when I get home tonight, I'm going to post this thing on the internet, on YouTube, and you can catch the end of it, all right? I just don't want to skip some of those things because you need to know what you need to know. All right, connectors, mechanical connectors. All right. For the most part, you're going to, right now, these days, you're going to be dealing, well, there are some different ones because there are different profiles of the tips as well. But two types, SC and LC. Okay. SC stands for standard subscriber or subscriber connector. Yeah. How is it constructed? It's got something that's called ferrule. Ferrule. And ferrule is that tube that you can see here, and it goes all the way through, and it makes actual physical contact with that optical fiber strand. And everything else is a housing. So this would be a ferrule right here. This would be a ferrule right here. This would be a ferrule right here. Now, the difference between these two, for the most part, and here's something that's called lucent connector, or sometimes it's called little connector or local connector, but lucent seems to be the most popular name. When they, as I say, they figure out what they mean by the L, let me know. Okay. But lucent is the one that is mostly used, or quite often just kind of LC. The biggest difference between these and these is the size. These are a little bit bulkier and thicker, and this is not as thick, it's thinner. And you know what, believe it or not, it matters. The size matters here because if you have a lot of those thinner, smaller connectors, you can fit a lot more in the rack space than these. And if you have huge companies that are employing a lot of those, and they have closets upon racks in the rows, then if you add those, then the space is going to be way better conserved. So this is the newer one, but these are also being widely used. And this is the ST connector. This is one of the earlier ones. Well, you might see that in a museum or in some of the way old installations. Now, typical wavelengths. While it is common, remember what I talked to you yesterday, it is common to use frequency in hertz to specify transmission bands in radio communications. Optical fiber communication is set to use wavelengths in nanometers. It's just the way things happen to be. Now, here's the typical wavelength. What is it? You know, the light is the winner, as Vince said, but not without challenges. Right? Let's say what I hear. Optical communication relies on transmitting the signal in the form of the light through a translucent medium, glass, or sometimes plastic, some of the newer ones. Ideally, the scenario would seem as following. Shine the light through the glass rod, shine the light through the glass rod, and receive it on the other end. Simple idea, right? In reality, the efficiency of the transmission is related to wavelengths of light. Well, as opposed to just straight attenuation, which is straight signal degeneration or signal deterioration, because of course, the longer the fiber optic strength is, the weaker the signal is going to get. That goes to the other end, right? It's not, well, it's not going to go on forever. Right? Now, for the transmission to be most efficient, it needs to bear at least the least amount of obstacles, such as what works against us? Attenuation, which is I just talked about. And then, who was it that talked about the colliding of the, was Ben, yeah. Scattering and absorption. It's not as much the photons or the light particles interacting with each other, but interacting with the medium it travels through. Now, let's see here. Come on, work for me. Attenuation. So we talked about that. Well, we're traveling through a physical medium. The further it goes, the weaker it's going to get. We get scattering. Well, the light beams or the light modes or the light particles are traveling through, and this will be highly magnified glass. It will be glass particles. And sometimes they're going to hit those glass particles and they're going to just bounce off and scatter. So scattering is something that works against us. And here is the dotted line showing us the scattering. So here's the attenuation. And here is the wavelengths. So this will be the high frequencies. This will be the lower frequencies. This is basically still within the infrared. But look, if you have 850 nanometers, the scattering occurs way more than if you go to the lower frequencies there. So here is the curve that picturize the scattering of the light. All right, the other one is absorption. No, I'm not going to read that here, but I'm going to explain this to you. Certain frequencies, when interacting with water particles, where do we get the water from inside the glass? Oh, no matter how careful you are, we're living in the physical world. We're not living in the computer world. There is always going to be some moisture that is going to be trapped while producing the glass. And it's enough of that some of the, it's very small amount, but still enough to cause us trouble. Well, how does that work? The moisture that is there, sometimes, somehow, with certain frequencies, it is going to basically absorb the light and make it disappear. And that's it. So here's the absorption. Here are those two nipples right there. Between 850 and 1300 nanometers, here's the peak of the absorption. So if you try to send light with that frequency or that wavelength there, don't send it through the fiber optic because you just won't see it at the other end. That light is just going to be absorbed by the moisture that exists. It's trapped in the optical fibers. And another peak is between 1300 and 1550. That's the absorption. So this works against us. And now here, the scattering gets low enough that we could use that region. Actually here, we could use this region here, 850. So it's a bit of a scattering happening there, but you can still send the light through. And over here between these two humps, you can still use that frequency because the scattering is way lower and there's no absorption. So here, that's why we have those typical wavelengths that are associated with fiber optic transmission. Now, we humans wouldn't be humans if we saw a challenge and, if we didn't try to overcome that. So I'm going to read this part here. As technology progresses, the fiber optic industry is implementing RWPF and ZWPF, so which stands for reduced water peak or zero water peak fiber. So some of them are being produced already that are getting rid of that problem. And those fibers are considered as full spectrum transmission optical fiber because there is no water absorption. And optical fiber primary transmission wavelengths 850, 1310, 15. For the most part, there are some companies that are using slightly different frequencies. Okay. And here is the scattering versus absorption. Here in industry implemented typical wavelengths. All right, so here's the plastic optical fiber and multi-mode, see, graded index and single mode, multi-mode and graded index. So plastic optical fiber, typical wavelengths, 650, see that? That's even here somewhere, and 850 nanometers, typical wavelengths of transmission. Multi-mode and graded index, typical wavelengths of transmission would be 1850 and 1300 nanometers. And a single mode would be 1310, then would be 1490 to 1625 nanometers, but typically it will be 1550. That will be the most common wavelength that is being used to transmit signal. And that's it for today, guys. Clearly the light is winner here. I should make my screensaver, or that should be the our motto for the rest to the rest of the semester here. Okay, cool. Thank you very much. You guys are wonderful, and I will see you when I see you. Cool. And oh yeah, we still have some labs. Okay, bye guys.